take it away.
Hi everyone, I'm very excited to present this. I think this morning actually provided kind of like a great motivation for my talk today. And this project is a collaboration between myself and James Finley at USC and Max Donelan and Suravi Sima at Simon Fraser University. And the title of my talk is More Better? Evaluating the Role of Experience in Energy Optimization During Split Belt Adaptation. So as everyone in this crowd basically knows, assistive devices are designed to reduce the energetic cost of walking. And here we have some pictures of some of these devices designed by people here. But whether these devices are being used and allow people to reduce the energetic cost of walking doesn't only depend on how good the design is, but also on whether people actually learn how to take advantage of the assistance that these devices are providing to reduce energetic cost. So in order to understand kind of like these adaptive locomotor processes that actually help us reduce the energetic cost of walking, we need to explore how learning is occurring during locomotion. And a common approach that we actually use to study locomotor adaptation is the split belt paradigm. So to date, and based on what we mentioned this morning, this idea is that adaptation usually has kind of been achieved when we achieve asymmetric behavior between limbs. And the paper that kind of kick-started this whole area of research of using split belt treadmills was the paper by Darcy Reisman in 2005. And in this paper, she basically said that when people adapt to a split belt treadmill, they will go from having asymmetric step lengths on each side, so on the leg on the fast belt and on the leg on the slow belt, and then these step lengths are going to converge towards the same distance. And that means that once they achieve this symmetric behavior, adaptation has occurred. So basically, she claimed that adaptation of interlimb parameters is basically, or the goal is to restore symmetry to the gait cycle. So kind of based on this idea, there has been tons of research in which they define kind of like the milestone of adaptation to be achieving symmetry. But before I continue, though, as reviewer number 2 in our last paper said, step lengths can be defined in many different ways. So I just want to make sure that we're all on the same page when we talk about step lengths. So the step lengths, the way we measure these during split belt walking, we have markers located on the ankles, and we're going to define step length as the distance between limbs at leading foot heel strike. And therefore, this value of step length asymmetry is going to be the difference between step lengths normalized by the sum. And specifically for split belt walking, we usually do the step length on the fast belt minus the step length on the slow belt. So therefore, when we're walking on a split belt treadmill, we're going to go from negative asymmetries, meaning that the step lengths on the slower belt are longer, to asymmetries that are around 0 because both step lengths are of equal length. However, there is also another possibility of the values that these asymmetries might take, and that would be positive asymmetries, but these asymmetries have actually never been observed until now. So in our last paper, we actually gave people visual feedback for them to walk with this kind of like these different patterns of asymmetry, negative, 0, and positive. And what we found is that after people had experienced this landscape of step length asymmetries, when we let them adapt, they actually ended up adapting towards positive values. So again, this does not occur during typical adaptation experiments, which are usually around 15 minutes. So just for comparison, here in green, I'm showing like our typical adaptation curve, and you can see how after experiencing the landscape, our adaptation curve was very different from what is typically observed. So the reason why we concluded that this might be happening is because when people walk with positive asymmetries, taking those longer steps on the fast belt allows them to reduce the amount of positive work that is being generated by the legs and reduce metabolic cost. So here, on my x-axis, I have step length asymmetry, so it's going from negative to positive, and on my y-axis, I have the work rate generated by the legs, and we can see that as asymmetry becomes positive, individuals are actually reducing the amount of work that the legs are generating. And also, we see that for lower metabolic costs, that means that there is less positive work that is being generated by the legs. But the question is, do participants naturally converge towards these more optimal strategies? So our experimental protocol was very simple. We just had people walk on a split belt for 45 minutes, no breaks, continuously. We measured metabolic cost, and we measured the location of those ankle markers and ground reaction forces, and we tested 15 people. So for our results, here I'm not gonna show asymmetry, but actual step lengths. So what we see here is in red, so hot, is the step length on the fast belt, and in blue, which would be cold, is the step length on the slow belt. So usually I'm going to show results at 15 minutes because that is what is traditionally used for adaptation. So you can see that the step lengths start very asymmetric and then they converge. And if we ended our experiment here, we would say, yeah, these converge. But we actually, for the extra 30 minutes that we gave them, we see that the step lengths diverge again. And actually, the step length on the fast belt was about 6% longer than the step length on the slow belt. So similarly, participants continuously decreased the positive work that was performed by the fast leg. So here my dashed line is the work at 15 minutes, and we can see how throughout this complete 45-minute adaptation, the work from the fast leg continues to reduce. And in fact, we saw a significant 11% reduction in positive work from the fast leg when we allowed people to walk for 30 more minutes. Finally, so we also measure metabolic cost. So here, this solid line indicates the cost of belts tied. People always want to know if the cost of split belts is similar to the cost of walking with belts tied, so that's our reference here. And here we see how our metabolic cost continues to decrease throughout the entire adaptation. So in fact, we see a 6% reduction in metabolic cost when we allow people to walk for those extra 30 minutes. So we used our data and we fit a single exponential model. So basically what we see here is this term would be, so if my time was infinity, if I let them walk in there forever, they're going to end up at a metabolic cost of around 2.18, which is indeed larger than the cost of walking with belts tied. But what we can see here too is that this term is pretty close to 45 minutes. So if this t-value of time was equivalent to those 45 minutes, we would see that people are actually pretty close to the lowest metabolic cost. So what are the take-home points from this talk? So taking steps of equal length and symmetry is not the goal of split belt adaptation. It's just kind of like a path on the road towards a more optimal strategy. Participants adopt step length asymmetries when they are allowed enough time to walk on the split belt treadmill. And adaptation actually involves fine-tuning of walking mechanics to reduce energetic cost, and this process takes significantly longer, at least 3 times longer than what is traditionally allotted. And with that, I would like to thank both our institutions and our funding sources. Thank you.
Okay, I'm going to ask the first one. What do you think the objective function is? And then I'll pass it to the back.
Well, I think for such a long task as 45 minutes of walking, it's probably energetic cost. Because you need to kind of be able to use enough energy that you're not exhausted.
Would an amputee show the same result? Based on an earlier talk we saw, amputees don't seem to be optimizing for metabolic cost, so I just wonder.
Yes, no. So I think, well, so in an amputee, so there's 2 things. Probably their most important thing for them is not falling because it has like a more catastrophic effect. These are healthy college-age individuals who are pretty okay with balance. So I think it might be either a balance cost function, or it might just be because, well, I'll talk about this later with Steve in person because I have some thoughts.
Cool. It was a fantastic talk and really provocative results. So I guess I'll ask the question. Sorry, I'm Sam Burden from University of Washington. So I guess I'll return to the question that I wanted to ask before, which is the question Steve asked, which is, obviously the time scale of adaptation for people in all of these different variety of tasks that we're now increasingly studying with kind of human in loop are super important to characterize. And so you're kind of showing that the conventional wisdom kind of needs to be thrown out. You really need to do much more elaborate experiments. Any kind of general thoughts or rules of thumb about, well, how did you get to 45 minutes, and do you know whether an hour and 45 minutes just any general thoughts about how to arrive at when you think that you've really seen the adaptation horizon?
Yeah, so the 45 minutes were actually based on our landscape exploration experiment. It ended up adding to those 45 minutes the total time that we gave participants. So we just wanted to see if it was just like the 45 or that we explicitly told them take longer steps on the fast belt. But also there's a previous study that did a multi-day adaptation. And what they found is that after 5 days of adaptation, or yeah, like 3 days, it added up to 45 minutes as well. Participants also plateaued at positive asymmetries, but that's not what the study was looking for. So that was not like the take-home message from that study, but we just wanted to kind of like combine our study with that for the 45 minutes. Will they continue to reduce after that or continue to optimize after that? I don't know. 45 minutes on a split belt treadmill is a lot, and it's not super fun because we can't distract them because that will affect the adaptation process, but we'll see. We probably can like feed a model to predict if it continues to reduce or...
From Northwestern University. So I'm wondering if maybe the results of, because 45 minutes is not really a functional amount of time that people are normally, or walking, a lot of our functional daily activities are, less than 10 minutes or so walking from one place to another. Do you think that taking into account the time that someone is like designing a device for a long walk versus a short walk, that maybe their goals and optimization, like, or their cost function might change, or we should think about time?
I mean, and that's the whole role of energetics. I think we had this discussion yesterday, like you might not care about energetics when your task is really short, and whether you get really tired is not something that is going to affect you. Only when you do repeated exposures to that same task, or when you're doing it for longer periods of time, might you care about energetics.
Yes, hi. Thanks for the talk, Natalia. This is Helsi Torres Oviedo from the University of Pittsburgh. So question I had was kind of clarification question. So in the exploration task that you did in Journal of Physiology, the people walked also about 45 minutes?
Yes, so we had 7 different levels of asymmetry for 6 minutes each, plus the adaptation, so it was 35 plus 10, so it was 45.
Yes, so the question I have is like, can you contrast sort of like exploration? Basically, when you made them explore, it seems that it took them perhaps the same amount of time that when they didn't really explore, they just kept on going. Did I get that right?
Yeah, so one of the conclusions from our previous paper was in fact that when we force them to explore, they end up plateauing at the place where they would if they had done this task for 45 minutes. So now we know that they end up at the same place. So when we explicitly show them these positive asymmetries, they end up at a level of asymmetry that is basically the same as the one that we observe right now. Okay, thank you.